Thank you. So my agenda is basically, as I said, I would like to largely cover the ESC, but I also would like to touch upon the ABS and also how ESC plays the foundation for the the autonomous braking. First, just yeah. First, about brief about ZF itself. Following the acquisition of WABCO, ZF further strengthens its position in India with its manufacturing footprint, R&D capabilities, employee base, and aftermarket network in India. WABCO India's position as a technology leader in India adds significant value to the ZF brand in the country. WABCO India currently operates under the ZF WABCO brand, which is a unique value proposition that brings the best of both businesses to customers and will also further establish the value of ZF offering in the CV space. In terms of serving the full commercial vehicle sector supply chain, WABCO India has extensive and expanding market coverage nationally that is second to none. Yeah, as I said, it's ABS improves. Actually, it's the whole basis is on ABS. ABS improves the directional stability of the vehicle. All of us know it's improves the directional stability of the vehicle. Automatic traction control, hill start aid, and electronic brake force distribution is possible using ABS as a base. ABS paved the way for further advancement in safety technologies.
Can you just take a minute so I get this
connected? Yeah. I would like to briefly show a small video. Just a moment. You can also see the other slide, other video. Yeah, what these two videos actually tells us is that it's not adequate that if you have only the directional stability, which ABS provides, the lateral stability, which is called roll stability, and vehicle skidding, which is called yaw control. These are very important to keep the vehicle stable under very dangerous driving conditions. now I would like to briefly tell you what is the actually situation in India as far as the accident data is concerned. So out of 62 lakhs kilometers of roads in India, about 5% is actually the national highways and state highways. And which accounts for almost 61% of the road accidents. Road accident related death, actually the fatalities, remaining 39% road fatalities occur on 95% of the other type of roads. Vehicle densities have significantly improved. I will show the next slide. You can see the actual data. Vehicle density have significantly improved, almost 75% at 40 vehicles per kilometer today. The technologies implemented so far have stabilized the, as you saw in the previous slide, to a level of 150,000 fatalities per year. Not a good number. I think India holds the dubious distinction of the largest number of road fatalities in the anywhere in the world. Even though we are only about 1% of the vehicle park, I think about 8% of road accidents happen in India. So the technologies implemented so far have will stabilize the fatalities. But we have a long way to go. It has been stabilized despite the poor infrastructure and very high vehicle population growth and the increasing power, the power and speed of the vehicles. Yeah, now I come to the electronic stability control itself. As I said earlier, that ESC is the first step towards autonomous driving. Yeah. It automatically intervenes to improve the vehicle stability against roll and skidding. It's unlike ABS, which actually comes into effect on very panic braking conditions. On those critical incidents it comes. But in the case of electronic stability control, it actually monitors the on a real time the stability of the vehicle, and then it intervenes whenever the vehicle becomes unstable. Automatically intervenes. I would say in a way it's like a hand of God, to the driver, because without his recognizing, this actually constantly monitors the stability of the vehicle and applies the brake or intervenes in an intelligent manner and brings the vehicle to control. That essentially is the role of ESC. The system automatically applies, as I said, system automatically applies brakes on all wheels to avoid rollover. Selective wheels are also braked to provide yaw control to avoid vehicle skidding. The lateral acceleration, yaw, and steering angle are the critical inputs for the system to keep the vehicle under control. So the vehicle constantly monitor the lateral acceleration, yaw, and steering angle on a real time, and these are the key inputs for the vehicle, for the ESC to bring the vehicles to stability. Yeah. The closed loop system continuously monitors, as I said, continuously monitors the vehicle behavior around its vertical axis and automatically performs engine control or brake control depending upon the critical driving conditions. Yeah, the same. The closed loop system continuously monitors the vehicle behavior around its longitudinal axis as well, both in the vertical axis and in the longitudinal axis. And in the longitudinal axis, and automatically performs engine control and brake control depending upon critical driving conditions. So this is essentially explaining the way the control is affected on a real time. Yeah, now on the video. Yeah, I have a here. You can just see a video. Yeah, the video actually in this video, the ESC performs engine control and applies selective braking to control the yaw movement of the vehicle. System applies brakes on all wheels to avoid rollover. You must have seen smoke from the trailer wheels, in the video. Yeah, now coming to the testing. Yeah, India's first. Can I request all of you to mute your? I think there's an echo. So India's first and only ABS test facility till NATRIP developed various test facilities in India is this one. Sundaram Clayton long back had invested on a test track. It's about 40 kilometers from here. This was the only test track that was available in India till 2015. Even for the homologation of ABS, the entire country had to depend on the facility that we had. Of course, today there are a lot of much excellent test tracks are available in the country under the NATRIP scheme. This is a state-of-the-art testing and validation facility to carry out various developmental and homologation activities. Actually, the frugal engineering, best-in-class infrastructure, and rich experience of Indian conditions paves the way for fast adoption of advanced technologies. Actually, this is the approach we at WABCO is doing to ensure that all the global technologies are brought to India, or even technologies developed jointly with India and the engineers from Europe. Adopt what is required for markets like India, using all the best capabilities on software development and frugal engineering from here, and the advanced engineering competency of the colleagues in Europe. Indian road conditions are very unique. Any global system cannot be just like adopted as it is without proper refinement to suit Indian usage conditions. So we follow a unique approach to refine the electronic stability control to suit Indian driving conditions. Actual usage condition data was created by driving the vehicles pan-India, covering multiple terrains traffic and climatic conditions. This gathered data was filtered to arrive at appropriate fine tuning in the ESC algorithm. So it's the solution that we are offering in India, or what is required to be done in India, is essentially not what is available in Europe or any part of the world. It should be adapted and tweaked to the Indian requirements. That's a message. The database refinement helped to arrive at best-in-class ESC system to suit Indian driving conditions. An example of a double lane maneuver is shown here. And the left side graphs indicate lateral acceleration versus time. So with ESC off, so vehicle speed at exit is 69 kmph will lead to vehicle rollover. With ESC on, vehicle exit speed is 55 kmph due to system intervention, and vehicle is stable. Right side graphs, the yaw movement of the yaw movement of the vehicle is also controlled due to the system intervention. The threshold values are defined for every vehicle platform to arrive at final parameters. Yeah. Various, slide number 25, essentially various maneuvers are performed to simulate roll and yaw under different loading conditions of the vehicle. Same maneuvers are used during homologations to assess comparative performance with the ESC off and ESC on. Yeah. I have a few more slides to share on how ESC actually is a building block for autonomous driving. Yeah, ESC is the first step towards autonomous braking. You can see the, this is the stability control. That is the first step towards autonomous braking. Additional sensing devices like radar and camera paves the way forward towards autonomous emergency braking systems. So you have the basic ESC on which you build the further capabilities using the camera and radars and various sensing systems. In the previous slide, we saw a side radar on top of ESC. This can actually provide blind spot detection and automatic braking. So you have a side radar to handle this, to detect the blind spot and ensuring and also ensures that there is a vehicle automatically comes to brakes. ZF is a one-stop solution for sensing, processing, and actuation technologies to achieve level 4 autonomous braking. As I said, the basis is ESC. ESC, along with various ADAS technologies, are the enablers of next generation mobility. Towards better safety, fuel efficiency, vehicle integration, optimized vehicle integration, and for all these things, ESC works with the various advanced driver assistance systems and then builds that intelligence to provide those capabilities. Yeah, just ZF is a technology partner to bring next generation mobility. And now, yeah, this is more or less my last part of my presentation. So many developed countries have mandated various safety technologies, making the roads safer. And of course, in our view, the ESC is one of the very important and basic regulations that is needed to reduce the road accidents here. And adoption of various safety technologies have drastically reduced road accidents, road fatalities across EU nations. This is data from European EU countries. There's approximately about 36% reduction in the road fatalities in EU 27 over a period of last 10 years. And that completes my presentation. So we have, I think we have another 15 minutes, so we can have discussions, we can take questions. Thank you.
Thank you so much, Mr. Kaniappan. We have few questions. So first, I would like to take the first question. First question is from Mr. Ajay Sankran. He wants to know, in the slide of side radar, if the vehicle detects a moving obstacle in its blind spot, how we can make it to detect whether that vehicle is stopping or we should stop to avoid mistakes.
Yeah, I am with me. I have some of my experts here, so I will take support from them. So Balaji, would you like to?
Yeah, thanks Ajay for the question. So yes, the side radar, as you could see in the slide, detects the object, or either it can be a pedestrian or a moving vehicle or even a cyclist, to detect the object. And in this case, as we explained, we automatically brake the vehicle, and that is the reason which we are saying that the driver does not need to intervene. So the ESC, or the electronic stability control, will be the fundamental the braking technology which will initiate the active braking. So when these side radars detect the objects, it communicates back to the control unit that there is an object detected, and the respective message will be initiated to make an automatic braking. So driver, when it actually goes to a level of around the autonomous level 2, level 3, he can be comfortable, and the complete system will actually take care of the automatic braking of the vehicle.
Thank you. Essentially, here the logic is, you have sensing systems, think, so sense, think, and act. That's a basic thing. So the input from the sensors get into the ECU, so it provides the required intervention to the braking system. Yeah.
The next question is from Chaitanya. He wants to know how ESP sense vehicle payload changes.
Vehicle payload change.
Thanks, Chaitanya, for the question. It's a very good question. So when we work with the OEMs on identifying the respective platforms, we actually try to work on the parameterization, which means we need to understand what is going to be the highest payload based on the GVW of that respective vehicle. And we actually try to take the platform in such a way we go to the maximum threshold limit in understanding these parameters, and then homologating the vehicle to that extreme parameters. So naturally, a vehicle of a GVW of 16 ton can have a maximum payload can be calculated. And now we also have other regulations in India due to this the payload requirement, where each axle can also carry this extra amount of ton. So these things are already pre-calculated while taking that particular platform in the alignment with the OEMs. These two important factors will be considered for arriving at the parameter. So finally, the threshold parameters will be tested, homologated, and that will be given for that particular platform to the OEM, which will be flashed on the vehicle when it is being rolled out. So this naturally prevents the the rollover or the or even the change when the vehicle even achieves its maximum payload. And this is being taken care in the way that I have explained now. Hope I have answered your question.
Mr. Kaniappan, you want to add something, or should we move on to the
Yeah,
second?
we can move on. We can move on. Yeah.
So the next question is from Mr. Sachin Dete. He wants to know how much speed reduction is allowed after ESC intervention. How does it monitor on actual vehicle?
Yeah. So if I understood your question right, so you would like to know that what is the maximum speed reduction when an ESC is actuated. So if my understanding is right, I would like to answer it this way. So the system, the ESC actually intervenes, or the stability control intervenes, not based on the speed, irrespective of the speed. When the vehicle is about to topple or roll over, it actually senses with the respective systems, which is actually part of the stability control. So it does not matter at which speed it is, even at a speed which is even to a lesser of close to 20 kmph to a speed of around 120 or 140. Practically not possible with our commercial vehicles in our roads, but still the speed is not a major criteria, which is only the input which will be taken in the calculation of the rollover. So speed is not a criteria which will actually decide that what is going to or when the ESC is going to intervene. All other factors like the CG and all the geometrical dimensions of the vehicle without payload and with payload is all what matters.
Thank you. The next question is from Mr. S. Mohan. He wants to ask, how can we detect any deep pothole for ESP control?
ESC does not detect the deep pothole or any potholes in our road. For that, meaning even the ADAS systems, whatever the sensors which comes in the radars or cameras, are there to detect the objects, probably metallic objects or human or cyclists or pedestrians. Generally, potholes are something for a commercial vehicle. I think a pothole of a normal size in our roads are something a commercial vehicle can just sail through. And if it comes into a pothole which makes the vehicle roll over because of getting into a pothole and then the actuating speed, the ESC system will actually intervene and then take control. But not it cannot detect a pothole. Probably after getting into a pothole and then actuating, there is a way that a vehicle is going to roll over, the ESC system intervenes. But the ESC system cannot detect a pothole in a road.
Yeah, it's not required to detect as well for this purpose. Yeah.
Okay, in the interest of time, we'll take one last question. This question is again from Mr. Sachin Dete. He wants to know, how does the wheel selection is happened for braking to generate corrective raw moment?
Yeah. So yeah, thanks, Sachin. So in terms of the wheel selection, how do we categorize this? Based on the vehicle geometry and where it is going to get a rollover, we would know that what is the pressure or the we have the wheel speed sensors as part of the ABS system itself. So we would know the speed of the wheel, and we understand what is the pressure of braking to be applied through the modulator walls to which part of the wheel. So it is an intelligently actuated system where the algorithms are built in such a way that knowing the pressure on the respective wheels, the equal amount or the equal amount of the pressure is being pushed to the wheels, so that all wheels get an equal pressure to make the vehicle stable. So the system takes care of understanding to which vehicle wheel the maximum pressure should go, to which the lesser pressure should go. Accordingly, the system will actually open out to certain valves the respective to the amount of pneumatic pressure to the system.
Thank you so much for giving your time for the question answers. Thank you so much, Mr. Kaniappan, for joining in
Thank you.
today. Moving on, before I introduce the next speaker, Vivek, I would like you to play the highlights of our track day event. Thank you, Vivek. Now I would like to invite Mr. Sathish M. Mr. Sathish M is the DGM at Ashok Leyland. As head of vehicle dynamics attribute engineering team, he is involved in evaluating the aspects such as ride comfort, handling, steering wheel, gear shift quality, drivability, braking, and driver ergonomics on commercial vehicles. Over to you, Mr. Sathish.
Thank you, Deepanshu. Hope you are able to see the screen and hear the audio.
Yes, we are able to see your screen and hear it.
Okay. Good morning, one and all. Present here. The topic I'm going to present is on vehicle dynamics in the commercial vehicle segment. Before getting into this, first of all, I would like to express my deepest gratitude to all the people who, through their encouragement, support, knowledge, and patience, enabled me in starting and continuing this journey on vehicle dynamics. Now I feel it is my duty to share my experience and knowledge. For this, I also would like to extend my gratitude to the organizers and the Ashok Leyland management for giving me this wonderful opportunity. Vehicle dynamics as a subject and of study and practice is a vast ocean, right? So typically when you set for a journey, you start with a map. So I believe this is a typical map which will help you go through this journey and understand in and out of most of the vehicle dynamics attributes and parameters. Now this talks about the interaction between the human vehicle and the road, and then so typically the driver gives an input into the control, and the this control is further transmitted to the further vehicle subsystems, either through electronically or mechanically, and then that has some responses, and that interacts with the road, typically with the tires, and they interact in the vertical direction, in the lateral direction, and the longitudinal direction, and the vehicle makes a move. Now, the first response the driver sees is visual. So if he takes a turn, he will see the vehicle getting turned. So visually, he'll see the vehicle getting a turn. And it also moves forward. And there is one other feedback which comes through the seat. That is, in case of if there's undulation on the road, then you will see some vibrations depending on the suspension, how it negotiates the undulation. you will see also vibrations. When you are taking a cornering, you also see you are being pushed to one side laterally, and then your seat will support against it. So this is another feedback which you will get. Now this is an interesting communication which comes back from the vehicle. Now another interesting communication is, or very interesting communication is there from the controls. Unless otherwise you sit in this driver seat, you won't perceive or you won't know about this. Typically what comes from the seat is also experienced by the driver as well as co-passengers. In case of buses, it is also the passengers of the buses. But when it comes to the control, the driver, he himself experiences this. But one important phenomena that happens is most of these are subconscious. It may not be very obvious, or when you typically drive a car or a two-wheeler or whatever vehicle, you get all these feedbacks, but you won't be having thought about it in general. And all these feedbacks comes in a very subtle manner. Now, for example, if you steer a vehicle, when you steer, I mean, there could be some, when you negotiate a corner, and then as the corner increases, you sometimes sense there is the torque feedback coming in the wheels, and this is sensed by the driver. Now, if you give a complete assistance, typically in a commercial vehicle, it is assisted by hydraulics. So if you give full assistance and you give an input, and then the hydraulics takes care of most of the part, and then there is no feedback that's coming at all, you will see that as a plain control. And in general, drivers perceive this. They may not be able to tell you exactly, but they'll perceive this. The feeling is, I mean, very blatant, or I'm not able to control the vehicle, because when you point towards a direction, you may sometimes you won't, because the relationship is not there between the controls and the input, you won't feel it that the vehicle is going to turn this much. So you may go give a larger input, and then you start overcorrecting it. So precise controls may not be possible. Similarly, for example, in the gear shift, I think this most of you would have experienced but not paid attention to. For example, if you shift a gear, you exactly know once the gear gets engaged, you'll get a positive feedback, and then you stop the action. Or when you come out of a gear, you know at various stages that there's a feeling coming from your hand, and that communicates with you and then tells that something is happening, and something is happening right, and you are feeling confident of it. And takes one other example, the pedals. For example, you accelerate, and in this case, the acceleration typically nowadays all the vehicles come with electronic control, ECU controlled engines. So therefore, there is no proper mechanical connection between the input to what you give and what you experience as a feedback. All these feedbacks are engineered in the pedal itself. For example, when you press a pedal, in relation to the travel it takes, there also should be a force feedback. Typically, these feedbacks are engineered by providing springs and by providing the travel, how much travel it should take. And then for end stops, for example, rubber end stops and other things. Similarly, and very, very interesting thing in a truck is the brakes. So when you apply the brakes, typically what you do in the pedal is open up a valve, and that valve further open up other things, remotely operates other valves, and then it operates the brake. Now there is no mechanical connection in between, but when you apply a brake, if there is no relationship between the pedal input what you are giving and the G level what you are sensing, if there is no relationship, you won't feel confident about the overall braking. So you may end up getting a higher force feedback, but the vehicle may not stop. Typically, but the vehicle still has a stopping power. But driver will feel this as a perception of poor braking. He will end up saying that this vehicle is not good. The braking is not effective. Although it has a power to stop the vehicle, the feedback which is coming from the pedal makes him say that it is not good enough. It's not good enough. Similarly, clutches. So everywhere there is an assistance technology, typically in all the trucks. So this assistance isolates you from mechanical feedback. At the same time, you should get a feedback. So driver should be getting. So this is mimicked using various stiffness of springs or bump stops, rubber bump stops. So in general, if you commonize or if you generalize all these expectations in the controls, there are three things which comes to the mind. First is the safety. So you should always feel that the controls are safe. You shouldn't get stuck. You shouldn't get a shock load. So you should get a sense of safety at first. And then comfort. So all these controls, typically driver holds this or operates this continuously during driving. And in a day, sometimes trucks covers around 400, 500 kilometers. So in all these things, they should have a minimal fatigue, impact on fatigue. So you cannot have larger efforts. At the same time, it should also give a feedback. Now coming back to the last point of giving confidence. This is one of the most important things. While ensuring lowest level of forces to ensure that this is comfortable, we also should give a feedback of or a sense of feedback control that gives overall confidence. Like I said earlier, you apply a brake, the pedal moves, but you are getting a higher force level in the foot, but the vehicle is not stopping yet. If you still more apply the brakes, it may end up in full stop, but since you are getting a feedback, you won't feel confident about the braking at all. This happens even in steering. You can try to get this feedback. Typically, if you drive back-to-back different car from different OEMs, you may sense this immediately how they have their brand statement and how it is set up. So typically, when you take a corner, as the corner as you increase, there'll be increase in the force, and when you come to the center position, there'll be a reduction in the force. And when you go even over a straight line, you should get a feedback in the steering wheel saying that it is you are remaining in the center region and it is not going too far away. If the center region is not identifiable, you may not feel a confidence. So you may feel that you are giving a constant correction to the steering. This happens everywhere. So to sum it up again, the expectation will be safety, comfort, and confidence. Now, applying this for individual systems, the safety, comfort, and confidence to various individual systems like the suspension, the steering, the gear shift, the engines, and the brakes, we come up with these verticals like ride and handling, shift gearing, steering feel and response, gear shift quality, drivability, braking. This we call it as a major attributes, and then these major attributes again applied to this individual topics of safety, confidence, and comfort. Will further you can detail into a further sub-parameters, or we call it as sub-attributes. I have listed down some of the key sub-attributes here. In case of ride and handling, bounce, roll, and pitch. For example, if the vehicle rolls, if you negotiate a corner, you go over a corner and then the vehicle typically rolls, and then depending on the amount of roll you experience, you may get a sense of safety, or you may feel unsafe about it. And for example, you apply a brake, the driver applies a brake, either you as a driver or as a passenger. If there is a diving or a pitching happens, then you may feel little more unsafe about it. And the other behaviors or the attributes could be isolation. For example, you go over a speed bump and sometimes you won't even feel about it. Is it a good thing? Is it having a complete isolation is a good thing, or the driver should have some sense about it? I think ideally you should have some sense that you are going over some pothole, because in case of slow maneuvering, if the tires goes over a stone, you should be able to identify that it is going over a stone. If there's a small curb and you're trying to have a tight negotiation, you should know when you are going over a curb, or when you are going over a stone, or when you are going in the normal road. So for this matter, you should get feedback in through all the things, either through suspension or through the steering wheel or through your pedals. So complete isolation is also not good. At the same time, a complete hard and impact field is also not so good. So you typically assess this as an attribute and then find out how the vehicle stands. Overall stability. Again, if you set up your vehicle too soft, it'll be very comfortable, but as a driver, when you go over different terrains, you may not like it because there is a constant motion in the cabin or the motion in the overall vehicle. And this almost feels like it is an unstable platform. And once there is an unstable platform, it ends up in a lot of other things like motion sickness and many other things. So that is also not so good. So there is one another parameter which is typically evaluated during the ride and handling assessment. And then coming back to the steering feel and response, maneuverability. So typically you give one steering input and how much steering wheel input. And in trucks, you'll have 2.5 turns, 3 turns per side arc. So based on that, you will find out how much amount of steering you have to give typically for a corner. For example, in a 90-degree T junction, how much you are giving to negotiate that turn. So it's called maneuverability. But to pass the norms or to I mean, because in some cases to even manage the cost, you will end up in a steering gearbox, which will have a deeper ratio, and sometimes it becomes unavoidable. So you have to have an ideal balance between those. And then, as I told you, on-center feeling. This is when you go over a straight line, you should know exactly where the center position of the steering wheel lies. You go a little bit to the left or a little bit to the right, then you should get a slight increase in the effort, and that gives us a lot of confidence about it. Then steering sensitivity. Again, the more you give a steering input, there should be a proportional increase in the torque or the force also in your hand. If it is not there, I think we discussed in detail. If it is not there, it won't give a confidence to the driver. And then inadvertent steers, for example, bump steer and brake steer. You apply a brake, and then because of the linkage and other kinematics coming into play, the vehicle may end up steering on its own. You go over a bump, and because of the suspension motion, you may end up in a change in the steering course, and therefore you may feel it uncomfortable or unsafe. This is about a bump steer and brake steer. Now, ergonomics. Although listed under the gear shift quality, I think ergonomics play a very key role in the overall vehicle dynamics attribute. For example, you may have a steering wheel well engineered for giving a feedback, well engineered for giving you confidence, safe feel, everything. But if the position is not comfortable, then even it's not of much use. So every driver should be able to set it up according to his requirement or her requirement, and then ensure that the ergonomics is also taken care of. And this ergonomics applies to each and every controls, even the pedals, the gear shift. I mean, more in the gear shift, because slightly it ends up away from this one. And packaging plays a very challenging role in this, and therefore it ends up coming up in different products may end up in a different position. Coming back to the steering gear shift attribute, shift feel and select feel. When you change the speed, the gears, how much you are selecting. Typically in a truck, you may have a single set of gears, or sometimes you have low gears and high gears, and you may have to cross over a detent. Typically, when you engage the reverse gear, you should be given with a different feel. Typically, some cars you have to press vertically and then push it, so that you can differentiate between when you are engaging the reverse and when you are engaging the first gear. Or even within the gears, when you shift, how it go. When it should have you should get a feel of how the gears measures, and that should be engineered throughout the driving situation or the engaging situation. Typically, you will end up getting phases. For example, when it starts engaging, when it's engaging, and then when the engagement is complete and you are coming to a complete end stop. So all this is communicated precisely through your gear shift lever. If you are not getting this feedback, you may not have the confidence in the whole gear shift, and you won't know when it is engaged and when it is not engaged. Again, this increases the confidence level. And positioning, for example, by gate definition, the gears should be sufficiently apart. And then nowhere during driving you will look at the gears and then operate it. After a point, it gets into subconscious, and then you know by touching the gear shift lever or the knob, you know exactly what gear you are traveling, and then you can accordingly you will shift the next one. So this should be the communication should be very clear, and therefore the gate spacing and everything comes into play. That's also a very important attribute. Now coming back to the drivability, when I mean drivability, it is you give a response into the pedal or the throttle pedal typically, as well as the clutch, and then how the engine and the transmission responds to it. From the start to the end, from the engine up to the tires and how the vehicle behaves, and then how the vehicle is, the driver is feeling it fine. So when you typically do a start, you launch the vehicle, you engage the gear, press the clutch, engage the gears, find out the biting point of the clutch, then release the clutch. Depending on what vehicle you are driving, a diesel vehicle or a petrol vehicle, you give some amount of act pedal input, and then you start going increasing the speed. And during this increase, you also maneuver the pedal. For example, you give a input in the throttle, and then there should be a proportional increase in the RPM. And this communication is not only through mechanical means, it also from the by what you even hear sometimes. Typically, it happens in the drivability when what you hear as a proportional increase in the RPM and how it feels in the pedal. That also has a relationship. And if those relationship is not defined properly or engineered properly, it won't give a total sense to the driver. And then how the response is. For example, this is more of performance issue. So how the vehicle responds for different pedal inputs, say 10%, 20%, and then is there any proportional push in the vehicle? Depending on the amount of pedal and sense of acceleration. Whether it is giving a sporty feel, you put a full throttle, and then is it giving you a full sense of like a sporty feel in the acceleration, or is it very sluggish? Depending on the petrol, you may sense this in a different RPMs, but that is also a sub-parameter which typically is looked upon during the development of a vehicle. Now coming back to the brake feel and response, I think again touched upon a little bit. So you typically not even it's not simple stopping or releasing device. You may end up modulating. For example, you may want to stop at a different G level, although you won't be conscious about at what G braking you are giving. You may typically have a target position where you wanted to stop, and you first start smoothly increasing the G level, and then as it approaches the target, you also slowly reduce the G level to ensure that it is smooth. For all these actions initiated by the driver, the pedal also should give an equal feedback to the driver, and also the vehicle should behave equally or proportionally. So for different pedal position, if there is a jerky response, you may not like it. So you have to have a brake, proportional brake for pedal force and the G level decrease or increase. So this is typically called a modulation of the pedal. So for every input or every travel, there should be defined decelerations generated. Pedal stiffness, even between the travel and the stiffness, there should be some relationships. And force relationship, I think we discussed in detail, like between the force and the G level generator. Now, this is almost like a tip of an iceberg, I would say. Some of the attributes is listed here, but depending on the OEMs, depending on the segment where you are operating, and depending on applications, there'll be a lot of more detailed sub-attributes, and these sub-attributes will be seen in different means. We'll come to those little later. This is about different stages of development. So how typically in a OEM or in this case in a commercial vehicle segment, how we develop a product, and with a more focus on key attributes. That means this vehicle dynamics attributes. So typically it starts with the product positioning, benchmarking, and concept development. So during this stage, you will first figure out what we are going to do, where we should end up. For example, if I am taking say a tipper vehicle, who is there in the market presently, where should we target, what are the kind of technologies we should use, and if there is a closer vehicle or competition vehicle available, can we have a look at it and then find out what kind of characteristics they have, what is the typical definition or the full characterization of the attributes are. And then you end up recording all those things, find out what are the technologies behind giving this attributes or definition of these attributes. For example, you may not get the same relationships with different technologies. Say you have, for example, I would say, yeah, electro-hydraulic steering system. A normal hydraulic assistance may not you cannot tune the normal hydraulic assistance components to the level of electro-hydraulic. So typically this kind of technology applied in each of these systems is looked at, and then based on that concepts will be arrived. Typical problems you will see is, again, you may aspire to give a better vehicle, but you may not have the packaging for to support your architecture may not support. So you may end up in a different technology, but you may still want to achieve the target performance because it is decided by the market. You may want it to end up in a competitive, match the performance of the competitor. This is one typical response. And sometimes you may aspire a little more, and then you wanted to benchmark a truck which is not even in that market. So in case if you wanted to create a new segment, so you may end up looking at this kind of benchmarks not within the domestic market. It may be in the market or the developed market. Typically, you aspire to do a little more better, but in those areas or in those ecosystem, there'll be different suppliers and the different components which comes into play, and they have their own cost and other balances. So therefore, you may aspire to do that, but you have to do it with your own available systems. This is the typical challenges which we face. Coming back, the next stage is the virtual development. So once you are done with the conceptual development, typically what we do is develop models. That means virtual models, either the CAD and multi-body models. And then typically what happens is we developed a correlated model. We'll take a mule vehicle, do the correlation studies, those simulations, what we wanted to do, and verify all these targets, whatever we have defined in the conceptual stage or the benchmarking stage. And then find out whether all those things are, whether virtually are we able to achieve. Again, this is a thing, work in progress typically in this area and in the of vehicle dynamics. And during this stage also, what you do is you have limitations in the virtual systems. You cannot do everything perfect. There'll be a lot of gaps between the real world and this one. So you may end up in doing a lot of tunings in the physical world. So you also find out what is the base at which I have to fix, and what are the kind of tunables I should recommend to be produced. And then those are also decided at this stage. Typical challenges what we get is the inputs. you may not get all the inputs required for creating a subsystem and in detail. And sometimes you go for a new components, new technology, and for that technology, you may need a typical input from your supplier. And in case if your supplier is not able to provide with that, then you end up in assuming or guessing a lot of inputs. These are typical challenges you get. What kind of road I should apply, and what kind of terrains, how they typically in this terrain the customer will use. These are different challenges, and whether you can take a decision based on the numbers, because typically what you get out of this virtual stages, all either through graphs or numbers, or histograms and other things. Now, based on these numbers and other things, whether we will be able to judge the attributes or not. So this is also one another typical challenges we see in the attributes. And then coming back to the prototype. So this is where things getting a little more interesting. You start producing all the prototypes, components. So this happens in two levels. First, you check all the components. Typically in a component test lab, you find out what are the stiffness levels, and some of these inputs also are taken back to the virtual development to continuously be along with you to in case required. So you update all your performance graphs and everything, and then just check in the component level. I mean, you might have heard about this KNC, kinematics and compliance related studies. Put the car in a KNC rig and then find out a compliance or a subsystem in a rig, and then understand what exactly the prototype is behaving. Because till this point, it will be in a virtual stage. Now you will get a real prototype, and you may not reach the level of building the complete vehicle. You will have a subsystem in hand. So at this stage, you will test only as a subsystem and then take this further. You may go for a hardware in loop system or a software in loop system, and then try to further work on the virtual development, and then ensure that at this level, everything is fine. Then coming back to the vehicle level. And then here, typically, the vehicle is driven. A lot of data is acquired, a lot of tuning happens. The real development will happen at this point of stage. One another typical problems, which are challenges, I would say, comes in these stages. You may not have a very perfect prototype. You may end up with a prototype that is built for certain requirements, because everything is still in the drawing board. There'll be sometimes you use a mule vehicle, and then you fit a typical subsystems, and then try and tune the other required attributes or parameters. For example, suspension. If there's a cab suspension, and you may end up in putting the cab in a old generation of trucks, and then try and find out what happens at this stage, and whether we are able to tune and finalize the spec at a mule level itself. So you may not get that clear, perfect prototype, but still you have to work with this because to meet the timelines and the cost and other things. So once you finalize all these things, in all these things, there is a very, it's not done within the OEM. A lot of interaction happens within the departments, within the suppliers, and everybody plays a very key role at this level. And then finally, the pre-production validation. So you'll have a pilot productions, and then this is where you started getting a feel of the real product which is going to come out. So you will end up seeing what actually happens. One another things which I would like to mention here is a weight distribution. Say you start with somewhere, and then you may not know the clear weight distribution. What is the front weight distribution? In our case, how much will be the cabin front will be loaded, how much the rear will be loaded, whether the suspension stiffness is good enough to mitigate all those things, whether it will be, it will end up in changing the mid-load conditions. So all these things will come into play. And typically you will end up in the pre-production stage, you will get a good feel of all those things. And you may end up in last minute corrections, and other things will be happening at this stage. And whatever you do, finally, when it is sold in the market, the customer sees it completely as a different, in a different ecosystem. I mean, until this point, you may have a focused approach on particular attribute, and then you'll be seeing it. But when the customer sees that, he sees that from a different point of view, from the styling, from the ergonomics, from the operating economics. So a lot of things will be seen, and you will find out that there are some feedbacks coming, and then you may end up in doing a lot of refinements or initiating a lot of refinement. So this is how things, I mean, different stages of development will go. And the methods adopted. So there are, I mean, while doing all these things, typically these are the three major methods which we use during each development stage, called as subjective assessment, objective measurements, and then virtual simulation. We'll look at this in individual in great detail. So first is subjective assessment. I mean, yeah, I think you might have, if you're in this conference, I think you heard about this a lot. Many people talked about the subjective assessment. To start from the basic, yeah, typically what happens here is the driver or an engineer drives the vehicle physically in the real world condition, and then evaluates the vehicle in different parameters. And then based on that evaluation, typically or qualitatively, he will give a feedback about it. So these are more based on the subjective. That means his own judgment of it, how it feels. It's very, very important. When everybody will understand, it's like we saw in the first slide, it's all about the control, and until you sit in the driver's seat, you won't know how it perceives, how the control perceives. So typically everything starts and ends with the subjective assessment. So you start with understanding how your benchmark feels, and you end up in final product and how your customer feels about that product, whether whatever engineered, whatever you targeted, whether the customer is also getting the same feedback subjectively finally. So it starts and ends in a subjective field. So this is one of the very important tool or method, I would say. In this, typically there are different methods at which it happens, or at different stages it happens. So you may, for example, you may hire or you may end up in a field situation where you call different customers, key customers and their drivers, ask them to drive the previous generation of vehicle, the benchmark vehicles. We typically call this as a jury evaluation. So a lot of drivers will do location-wise in different applications, different terrains. Typically, you'll have a lot of terrains. And these are typical for a truck application. The left one is a complete mine road with curves. And these are the approach roads of mines. You might see this as this is a guard section, also combined with a rough road patch, a very critical corner. So you have a rough road. You may share the things with other fellow road users. This is a completely different aspect. This is a slushy road with a lot of water and mud and slush. And again, contrasting a plain and smooth road with high-speed corners, a wet road with a lot of gravels, icy conditions. So you may, typically, if you want to cover the broad spectrum, you may want to drive in all this aspect. There are some, in some respects, it's not only on road condition, there are specific tracks for it. Typical OEMs also will have their own test track setup, where you will end up having situations mimicking this, or which will simulate these conditions. So you'll have you will have a speed breakers, you will have troughs, you will have potholes designed in the test tracks. And typically, you may also drive there and then check. And then this jury gives a feedback. What happens typically? The jury gives a lot of feedback, and this have a varying degree of details. Some may say the steering is bad, and some may say the steering feel is bad. Some may say the torque feedback is bad, and some may say I don't like this. So there'll be a lot of details at which the typical jury will give you a feedback. Now it is up to you how to interpret, and there is no right or wrong here. But the final intent will be to ensure that the most critical and the important feedbacks are not filtered, and it is taken up to the design or the drawing board, and then based on that you taken design actions or attribute actions on this. So that is very, very important. So sometimes you filter too much, you may not end up getting all the feedback. But if you don't filter, you may get all the feedbacks, and some may not be relevant also. And sometimes the drivers also, based on their the way in which they communicate, the language in which they communicate, the intensity might vary, and you may get a different understanding. Now, to solve this problem, we typically add one more layer of evaluation that is called the expert engineers in their own development team. So typically, this will be a team of engineers who also drive along with the customer drivers, find out, observe how typically a driver drives in the field condition, and then based on how the usage patterns is, they will also drive along with them, understand what could be the requirement in this segment, and they will take a little more responsibility on behalf of these drivers, and then try to say, get the feedback, and then they communicate this in different languages. For example, typically, what is the real feedback, which is, or the control feedback which is coming, defined in terms of attributes, whatever we have seen, key attributes and the sub attributes. For example, how the launch feel is, how the steering sensitivity is. So they'll define this as each individual parameters, and then also say, this is what you may typically want to do. So increase this level or decrease this level. And also typically guide them in communicating, saying, okay, you may want to do the tuning at this position, or at this rubber, or at this elastomers, or at this springs. So like this, they may also point out, giving a little more engineering feedback. So typically, to avoid, again, to summarize, you get a lot of very different kind of feedbacks from the drivers, but to consolidate and to communicate that effectively, there'll be one more layer of engineers sitting in between, and then this team of engineers will actually, be an interface between the engineering team or the development team and the drivers. And it's very, nobody can say, again, as I said, there's nothing called right or wrong. Finally, it should the real feedback should end up this. And the scales, again, coming back to scales, in this chart, you're seeing a typical radar chart with what is expected as a target from this product, and how it performs, and how the competition performs. This is how you define the target. The scales here used is a 10-point scale. But depending on how, where you are going to ask this question, for example, in case of jury, if they are not able to differentiate too much, you may end up asking only 3 levels of question, whether you, is it good, okay, not good. Or you may end up in a 5-point scale, typically for a management jury evaluation. You may end up in a 5-point scale or 7-point scale, which will further get into little more detail. But when it comes to the engineering expert level assessment, it'll be in a 10 points. So this is how you typically do the assessments. So, and is all the subjectivity is good? Yeah. To support this subjectivity, there needs to be a lot of measurements. Although, there are a lot of debates and things depending on attributes, what you can objectively measure, and there'll be some attributes you may not be able to clearly measure, but still you will tend to measure, and then try to come to a closer measurement, which will communicate this to a driver, to the engineers who is developing the system, or the simulation engineer who is actually simulating the system, to improve the performance. Because you cannot unless you measure anything, you cannot manage. Typically, this is a statement, right? So you finally you want to measure. So you can see some of the instruments typically used in this one. So the top this one are this accelerometers, uniaccelerometers, triaccelerometers. You place this everywhere, typically in the kingpin, in terms of trucks, in the axle, just above the suspensions, above the chassis, near the engine location, and then capture the vibrations. This vibrations will, the intensity of the vibration, the frequency at which it happens, the way in which it gets transmitted, all this will be assessed using this vibration. And sometimes you also use string potentiometers, how the suspension travels. This also gives you a lot of indication. If you want to typically calculate the roll, you find out the left and right suspension travel, and then based on this you calculate the roll and then find out whether this roll is okay or not okay. These are the slip angle sensors. I think, yeah, to capture the slip angles at the body level or at the tire level. So you fit it and then you understand what is a direction at which the vehicle is typically going and what is a real inclination of the wheel or the tires. And then laser height sensors, again, between the what we talked in the string potentiometers, is more of relative displacement between two components, typically the axle and the across the suspension if it is axle and the chassis. But this is if you wanted to measure against the overall field. For example, a passenger will feel this as an overall roll against the road. So in this case, you may end up using laser height sensors, which will find out what is a body roll between the body and the ground. Then gyroscopes. So in case of yaw and pitch, you may end up using the gyroscope as a device. So this will find out about the axis how the vehicle travels. Typically these are velocities measured, and then depending on the requirement, you will be analyzing further to understand what is the jerk level or the acceleration. And the bottom one is the brake.
So Sathish, your audio is not there. We are not able to hear you.
Then coming back to the simulation methods, I mean, you do. I mean, we all know typically multi-body models are developed, and then in this case, it's a suspension travel. So you have a 6x4 truck with cab suspension, the vehicle suspension, the engine, everything modeled, and then based on this vibration level, whether is it acceptable or not acceptable, can we change the stiffness, can we change the damping level, whether the pitch is okay, whether the roll is okay, all these things will be analyzed. Typically for a steering system, this is again multi-body dynamic analysis for a twin steer. So typically you also one specific thing, one special thing we have in the truck is a twin steer models where you'll have the first two front axles are steered. So you may want to understand what is Ackermann performance. So whether to reduce the tire wear, you may have to tune the Ackermann performance. And then we talked about bump steer and analyzing the kinematics and compliances. Then find out whether everything is okay in terms of kinematics. And this picture talk. I mean, I think over the course of this conference, we have seen a lot of this picture again and again. There's a double lane change, and this picture actually illustrates the path of the corner. That means corner of a typical bus. So the top one is the front end of the bus, and then bottom is the rear end of the bus. So you give a steering input at this point. You will change, and then you come here, you correct the steering in between, to make a straight line and then end up again here to make the one more course correction. During all this maneuver, the typical expectation is you shouldn't touch the cone. You can almost see that the corner is touching the cone. And touching the cone or not touching the cone is one typical measure or things which we see. A lot more metrics are defined and analyzed, and then based on that, feedbacks will be taken. What happens typically is you end up driving the same vehicle again and again, and in the 10th iteration, if you are even a normal or a slightly good driver, expert driver, you can trick the vehicle to give so much of correction to the steering wheel, and even without hitting, you can pass that test also. So depending on the skill level of this one. So typically to control this situation, a steering robo is used to ensure that the intended path is given, and then for that intended path, whether the vehicle is passing the cones or not. Now coming to the complexity in terms of trucks. So unlike the typical vehicles of cars, you have multi-level of suspension. So you have the vehicle suspension primarily, the tires act as a isolation component as a mass and damping. And then you have the primary or the chassis springs and the dampers, bump stops. And then one more layer called the cab suspension, where you again have a lot of kinematics, again a lot of suspension. Depending on the configuration, there'll be a lot more configuration like front pivoted or front hard suspended in the rear suspended vehicle. And there are rigid cabs where you don't have any suspension at all. All the four corners are supported by bushes. And there is a complete fully suspended cabin where you have springs and dampers in all four corners. They have their own anti-roll bars. They have their own in-stops bushes. And this makes it more complex as well. Why you need the suspension in the cabin? Again, another challenge in the typical truck is the load change. Now, unlike the typical other vehicles, the change in the load is very, very vast. So typically for a truck, the unladen weight will be at around 4 to 5 tons, and laden weight will be around 10 tons. It's almost 2 times increase in this one. And then in the rear, it is much larger. It will be 4 times or 5 times between the laden and unladen condition. This gives a unique challenge, and you may want to, but you all have a same suspension, right? Yeah, there are technologies which might mitigate, which will give you room for mitigating all these challenges between the different extreme conditions. But in a typical high selling models, you still have a single the leaf spring, which will have to manage all this situation. So you have to work in both extremes and find out how it behaves in different load condition, in different terrains, and then choose your damper setting, choose your spring setting. And not only in your spring setting, because there is a large variation, your suspension become very stiff in the unladen condition. And to mitigate this, there's a cabin suspension. So this cabin suspension, again isolates you. Again, the challenge is not only as you add more suspensions and more travel, you also end up in heavy roll, heavy pitch, and all these things. Again, you will lose on stability. We spoke about it. You give more room for travel, or you give more room for motions. It will also end up in an unstable platform. It keeps moving, and then therefore the driver would. And this is, we have a lot of conversations we have had with drivers, and some of the Indian drivers, even though they have a lot of comforts in the cabin, they typically still like a rigid custom built cabin because of this feature. They always want to move along with the vehicle. If you have a lot of suspension, there is an independent motion, and this independent motion some way make them more uncomfortable. and therefore they end up liking a more rigid setting. And then there are a lot of variety of, for example, not only within the same platform, there'll be a lot of wheelbases. So each wheelbase will behave on its own. For example, a shorter truck will have a different braking response for a braking, and in a longer platform, you may have a different response. So, but in a typical situation, you may have to cater to the needs of the market. You may need a lot of different wheelbases, and you cannot have, for example, a typical engineers would like to reduce the variety of components, at the same time cater to the needs of a wide range of vehicle configuration. So you may again have a lot of trade-off situations, where you have to end up in laden condition, doing a trade-off for laden condition, unladen condition, and for different wheelbases as well. So these are the typical challenges we face in day-to-day life. And then there is one another unique aspect which we see in a typical truck is the lift axles. So you may not want all the axles to be in touching with the ground in all conditions. For example, to save the tire life, you may end up in lifting this axle. So these are one of the recent additions in the modern trucks, at least in the domestic market. And then typically what happens, this lift axle, suddenly when it changes, it also changes your lot of other behaviors. So you may have a different number of axles and springs coming in the during one load condition, and suddenly everything changes, including the steering changes in the other condition. So they also give a lot of, and all these suspension, for example, you do something in suspension, and you sometimes also come up with problems during the braking and drivability. So you accelerate and the cab is set very soft, therefore there'll be a lot of motions in the cabin, and this annoys the driver. You have a softer setting in the cabin, you apply the braking, the cab dives a lot, and that also annoys the driver. So you do one setting in one attribute or one subsystem level, end up losing in the other attributes or completely in other area. This is one another challenge typically faced. I think this picture almost illustrates many of the aspects of the truck. One thing I would like to point out is the role. This has since it's a completely fully suspended cab, this is one of the very early prototypes decades back. So you have a lot of role in the whole truck, and typically the drivers see this as a safety issue. So he turns, and depending on the rate of roll, he may sense it even as a safety issue. Right side is a normal in a straight line event how it looks like, and in a complete, when it negotiates a corner, how it looks like. This also you can see, the attitude is different, and the tires, how they slip, and then based on that, how much corrections the typical driver have to give. So just to give an idea of what can happen in a typical truck situation. Then coming back to the steering system, one another system. Okay, as we discussed, it'll be typically hydraulic, assisted through hydraulics. So you have to, and also there is one another norms which will say that without even assistance, this is the maximum load. This is the maximum load you can sense at the steering wheel. So you may end up in a situation where you wanted to give a lot of assistance, at the same time, without even assistance, it should perform well. And when it comes to assistance level, there are a lot more technologies available, but till today, the wide range of products goes with the plain hydraulic assistance, and you wanted to tune this assistance level to create a sense of safety and comfort, as we discussed, and confidence. So typically you will tune the pass curve. This graph illustrates a pass curve, how much assistance you need at what level. So this is the steering level, for example, how much you give input and how much assistance is given. So during the course, you can have too much of assistance within the shorter range, or you may have a sluggish range which will give a good feedback, but also end up in a different sense to the driver. So this is what we typically tune in a truck, and then try to give a right balance between the laden condition, unladen condition, and other things. One another illustrations of graph describing the relationship between the torque and the angle. So again, as I said, the inclination is one aspect which we look at, then find out how much inclination is good for the driver, or to get him a good feel and good confidence, and how much is more. So this is one another thing which we try to work on. And then hard point finalization, where we put the location of this ball joints, and within the there'll be a lot of trade-offs between choosing your Ackermann, choosing your steering geometries, at the same time giving you the right feedback in the system, and also avoid things like the bump steer and brake steer. So this is one another aspect where we work on. Again, put
Mr.
together.
Sathish, just to alert you, we are exceeding the time limit. I would request you to keep it a bit short.
Sure.
Thank you.
How much more time I have?
We have another 5-7 minutes, and then we have another speakers to.
Okay. Okay, I'll try to finish. So going, this is the most of the challenge. Yeah, there are a lot. We have seen a lot of configuration. We have a typical truck. We will have a lot of wheelbases. We'll have a lot of wheel configurations, and then have a lot of load body fitted into it. And then the challenges, as we saw in the videos earlier today, how typically the customers use and abuses this. And typically in a situation in India, in a lot of uncontrolled market situation, how the things are loaded. For example, a loose load, whether even after adding so much of things like ESP and other things, will it mitigate the problems of having a loose load? Whether a longer pipes or a very concentrated on how it acts. So these are typical challenges which we have to, going forward, we have to work on. I think I'll skip this slide, but only the point I wanted to make here is, we are moving towards a virtual world. To save on time and cost. Mostly the future is going to be definitely a virtual development, and the most of the efforts will get into this, where we have to do a lot of model development, refinement, and the correlation between this real and the virtual world. I think I wanted to spend some time on this for the person, or for the one, if you are new to this field of vehicle dynamics, or you are an aspiring engineer who want to learn more about this vehicle dynamics. This is some points for them. First, I would say that, yeah, aim for a full stack development. So as we saw, there will be a lot of assessment with the way in which you see at this. One is subjective assessment, one is objective measurement. You do a lot of virtual models, and you work on different technology. But if you wanted to really excel, or if you really wanted to understand the whole world, you should work on all of these aspects. Now, do you really need to get into a real industry engineering setting, or the real development areas or OEMs? No, you can even use your bicycle and understand these things. Even you can observe a lot of trucks and buses or other vehicles going in our vehicle. I have seen a lot of engineers doing this, and inspired by them, how they observe this and then end up working on real world, or in a typical industrial setting. So your observation is the key here. Whether you travel in a bus, you keep observing, find out what happens, how the driver is, you look at the driver, how he's doing all these activities. That's one aspect. And another is objective measurements. You need not end up waiting for expensive measurement tools and other things. You can even explore how this latest IoT technologies are. These are cheap accelerometers and other things. Whether we can use this as a tool to understand this. What is one another aspect. And virtual modeling, again, I very strongly advise you to work on developing your own models hands-on, not use the models of others, try with your own hand, and not necessarily with any very high-end softwares. Even start with a simple hand calculation or an Excel sheet or whatever, like tools like Python. I have one more slide giving you a thought about this. I'll go to the open source software where I have some thoughts about it. And then engineering and technology. Here, yeah, you need not really get all these things in an industrial setting. You can also look for the forums, magazines, and product literatures to get some understanding about the product, the components, and then use this as a starting point for doing your calculations and maths. And again, this is one software, a very interesting software which I come across, Open Modelica. What is this? This is a Modelica-based modeling and simulation environment. It is an open source, so even a student can use this. They are typically comes up with the drag and drop models. If you want, you can also get into a lot of detail and work on the equations as well. You can see them visually working on. You can work on the equations level. And if you want, if you have the means, you can also purchase proprietary softwares and extend this capability further, deeper also. So this is an open source software, but using the same model, you can put it into a proprietary software as well and then develop. And this software is very much integratable with other things like other softwares like Python, MATLAB, Julia. And therefore, if you want to do an iterative development, or if you want to understand how a sensitivity analysis need to be performed, then it can be integrated with others. And very interesting and important feature, I think, is going to be one of the new technology is a functional mockup unit. So you can extend this models. You can export this model into a functional mockup unit, and this, I believe, is a important technology because what happens in typical OE setting, you cannot share the model extend the model because it has a lot of proprietary content. So what this functional mockup unit does is, it will encapsulate all the models and the parameters, the inputs, everything into a digital model. It won't expose all the equations underneath. At the same time, you can share it and use it across all the other, and typically all the simulation softwares in the recent times, they have an interface for doing this. And this interface is standardized across the at different levels. So FMI 1, FMI 2, these are the various levels of standards which are getting implemented. So this, I believe, is one of the futuristic technology which will come into play. And very important when people work in a component level in the early stage of the programs. And then some more books. If you are a student, although there is nothing hard and fast rule to what you had to refer, these are some of the things which I have come across. Chassis design by Maurice Ollie, race car vehicle dynamics, Millikan, fundamentals of vehicle dynamics. These are wealth of knowledge. Please refer. Don't underestimate their power. Please read through this. They share a lot of fundamentals, and then they give you a lot of pointers which you really use in an industrial setting as well. Thank you. Thank you for your patient listening.
DT, you are on mute.
Thank you so much, Mr. Sathish. Now I would like to invite Mr. Girikumar Kumaresh. Mr. Girikumar Kumaresh is the Senior Program Manager, Lead Accident Research, India, Advanced Autonomous Systems Safety ADAS at Bosch. Over to you, Mr. Kumaresh.
Thank you. You able to see my screen?
Yes,
Hello?
yes, yes.
Okay, perfect. Okay. Let's start. Okay, thank you very much for giving me an opportunity to be with the team today and to talk about the electronic stability control and various aspects of it. And thanks for Mobility Outlook for conducting this conference along with FA India, Motion and Control 2021 Indian Vehicle Dynamics of its kind. So to set your short context, I'm Girikumar, working for Bosch since almost a decade now, and with overall experience of 15 years. And I've been working on accident research, and I had the team in India and ASEAN together, conducting commissioning of accident research and usage of this accident research in order to develop advanced safety functions and also understand the real root cause of accidents for a respective country. I hold a bachelor's in mechanical engineering, master's from IIT Roorkee, machine design expert, and has done a specialized course with accident research and on-spot investigation. So far, I conducted close to 3,000 plus accidents on the spot, and I've analyzed close to 10,000 accidents of various countries, and only in India around 6,000 accidents. So that's my short perspective and the background. Today, my topic is accident research and loss of control accidents in India, a perspective. Thanks to Kaniappan and also Mr. Sathish for setting up the base of the technology and also some part of vehicle dynamics, how exactly the system are in place and how it works and stuff like that. It's really cool for me that I revised my whole of my Thomas de Gillespie book, which I studied in vehicle dynamics and engineering, like all the steering mechanisms and everything. All these things is required to develop the certain technologies. So both the speakers touched upon the truck and the commercial vehicle aspect. Today, I will be touching on the car, especially the passenger cars, and in specific to loss of control accidents. Here and there, I'll just give you a short hint of what it is and how it is and stuff like that. So with this, I would like to go to the next slide here. I think accident research that really matters. Our motivation is to study the crashes holistically. And as Robert Bosch says that saving lives is much more important than the financial aspects of it. This can only be done by attributing all the three verticals or the pillars together, kind of infrastructure, education, and vehicle safety. If all these three topics are holistically approached, then definitely we have a very good understanding. This is my team, Central Corporate Research Division, and we are 16 people team. We take care of entire global accident research data. Again, we divide the global and the different units. And the head office is running in Germany, and I sit in Bangalore in India, take care of India and ASEAN, Malaysia, Thailand, Vietnam, and other countries. And we have commissioned, or we have an active data collection unit in of course, in Germany, GITAS, in Bangalore, in India, we have RASI, Road Accident Sampling System, Thailand with TAC, and even in Vietnam, we are commissioning accident research. And in Brazil, we have a new project in Campinas and other things. So in a nutshell, that the 6 people team take care of the global accident research, irrespective of the products, irrespective of the technology, irrespective of what comes next. So our main objective is to establish accident research data to have an in-detail understanding of how exactly an accident occurs, and then identifying the real root cause and enabling the different product strategies for that particular accident avoidance and mitigation. We have over 16 years of experience, and the team consists of mathematicians, physicians, and paramedics, and also engineers. We conduct statistical analysis and simulation for real-world crashes, and we take the data, do various kind of analysis to advanced technologies with AI, ML, and few other topics, and put this into product strategy for the specification of different business units within Bosch. And finally, we will also do a safety vehicle assessment of various topics, irrespective of which region the vehicle is and what product it fits in. And of course, I already covered, we have worldwide communication for the international expansion of the team. This is the core of our work. Visits anywhere, and we access the entire global data. So we have access to GDAS, we have FAS, MAS, US data, UK data, China CDAS, India RASI, and Brazil. Again, we have Campinas data, and most of the international data we have access. And this really helps us to pick up a very good understanding of how internationally different accidents happens, and then how to come up with various strategies in order to mitigate this kind of accidents. So you may ask me that is accident same? No, accidents are totally different, because we have different driving behavior, we have different vehicles, different rules of driving vehicles. So it's utmost important for us to really understand and also get into the regional aspect of the driver behavior to understand how exactly the accident occurs, and then only we will be able to identify new things. So the point is, even Dr. Kaniappan was mentioning, that we cannot copy paste the technology. That's really true, because the technology which is available in the Western world is designed for the Western world. In India, we have a heterogeneous mix of traffic. I have a bulla cart on my left, and I have a high speeding car on my right. Yeah. And in between, you have truck and CVs, which is running. So you need to design the whole system in such a way that you can handle this heterogeneous system. So that's very important. For that, we need really an in-depth accident data. And that's how we got into it. 10 years back, when I just joined this team, there was nothing in India. So that's where we started. You see the curve here, the curve, what you see here is the curve of the fatalities, which is 151,000. Which is released by the Ministry of Road Transport. And Bosch made an intervention somewhere here in the year 2009 and 10. That's where we started the first pilot study with 50 cases in Coimbatore area, along with an external agency. Then we brought in teams from Germany to be on the site. And for me, it was so exciting that directly after the college, I am on the accident site to really learn something new, kind of a Sherlock Holmes story, like identifying the evidences of trace marks, blood marks, and the skid marks, and the debris, and map everything and put together. So every case is different, and every case you have to solve it, kind of a puzzle. So this picked up, and which landed me today in doing accident analysis in most of the countries. And that's how Bosch started in 2009, and then slowly we had a transfer. And over a span of time, we could not do it alone, because it requires a multi-stakeholder approach where the data is used by most of the teams. So that's how we formed a consortium called RASI, Road Accident Sampling System. Now today we have 10 teams. I will explain you in the next slide what is this team does. And then based on this, we did various benefit estimation and assessments with respect to the vehicle safety and other things. So what you see here on the right hand side, the motorcycle ABS with 33% benefit, car ABS with 20%, ESC for around 13%, truck ABS with around 18%. So these studies has been published in SA International. I will provide you the links. You can download the research paper and get into it. It's all like 20-25 pages report with most of the statistics into it, and you have a different strategies how exactly this kind of analysis is done. Okay, so today I will get you into how exactly we do one particular loss of control accident. That's one type of accident. Okay. As I was talking about RASI, Road Accident Sampling System, this is not Bosch alone. It's almost like 80% of Indian OEMs and auto suppliers are in the team. We all pool in money together, and then we share the common raw database, and each of the team takes the database and they start working and they start interpreting their database for their own benefit. Okay, so this is a consortia where we all sign up together, spend same money, and access the same data. And if you ask me what data consists of like the scale pictures, images, reconstruction, feed photos, and different parameters. For one accident, we collect close to 1,200 parameters, which talks about what is the vehicle damage, how is the road look like, what is the weather condition, what is the injury status, which part of the injury status, and all the injury status is coded by abbreviated injuries called AIS. And also, you also understand what is the initial velocity, what is the final velocity, what is the delta we change, and everything. So this is how we get this data, and then we start developing and then do a detailed analysis. And we have teams collecting till now with Jaipur, Ahmedabad, Mumbai Pune Express Highway, Coimbatore, and Kolkata. So the team is stationed there. As soon as accident occurs, the team is informed by either by the police, either by the locals, or by their own communication channel. And the team drives to the nearest accident scene within 2 square or 3 square kilometers, covering all the aspects of it. And then we collect the data. So if you ask me that if I get an accident somewhere in the middle of India, will the team go and collect? No, my answer is no, because it's a sample stick study where you have a team predefined area, and we have selected strategically the areas in a way that it covers national highway, state highway, arterial roads, village roads, rural roads, and also some kacha roads as well in the whole of the system. And today we have 5 investigation area with around 5,540 fully reconstructed accidents, and nearly 8,500 vehicles involved in it. It includes all kind of vehicles, including bicycle, truck, pedestrian is also involved in it, around 1,000 pedestrians with close to 16,000 occupants. It's a vast volume of data which can be really digged upon. Okay, so this is a short intro of accident research, what Bosch does, and this is the form basis for most of the advanced methodologies and technologies what we develop globally. Okay, and we are proud to say that we also have a similar global methods for India. 10 years back, it was not possible because we were not in a position to even talk something about what is the root cause of an accident. Today, we can stand on together, and we have the data which is on comparable with most of the countries to select which product, which strategies work best for the India. Okay. So hold on your questions. Let's go to the second part of my presentation where I talk a little bit about the loss of control accidents. So today session is all about electronic stability control, right? So what is this product? How does product? Because you all know the technology much better. And the last 2 speakers explained vehicle dynamics such a perfect and pristine way that you all know what exactly the technology does and how it helps. But my responsibility today is more to do with how it is relevant for India and what that we see in Indian conditions. Is this really a product which helps for India? And if yes, what is the kind of percentage that it helps for India? This is what I wanted to give you a brief overview and brush through. And if you have any questions, just mark it. We will have an interesting discussion in the last. Okay. So to start with, what is loss of control accidents? I give you a hint for all the participants on the panel that you can identify a loss of control very easy in any of the streets. You just walk into any national highway or state highway. If you see a 3 mark with a semicircular pattern, like in this pattern, then that means it's exactly the loss of control accident, and you see it. And many people mistake that these marks are the brake marks, but that is not the brake marks, it is the skid marks. Okay, and for more information about what is the difference between skid and brake marks, you can check on my accident research basic videos, which is already there in YouTube. You will understand how exactly an accident investigation is done on a basic front. And the skid marks clearly say, so most of my accident analysis, when I go to the on the spot, if I see these 3 marks, that means it's 100% skid. That means 100% the driver lost control. Now my question is whether the driver lost control prior to the collision or post collision. Okay, so prior collision is that you have some obstacle, for example, a pole, a brick, or a pavement, or a boulder. You hit that and then do a counter steering, then you lose the control, then you have a 3 skid mark. Then that means the first collision has happened, and the subsequent second collision is the skid. In many cases, the skid happens just before the collision itself, and then the collision happens. So when you go to the accident site, you see a skid mark, which is very evident, but it's challenging to identify whether it is before the first collision or after the first collision. Yeah. So that's the overall point, and this is how it is. And before the first impact occurs, the car has a precedent skid maneuver, which can be evidently seen. and driver loses the control, that means he is trying to handle the car as tough as possible, but it is not possible. Now, I will also give you another hint. How do you identify whether the skid occurred prior to the collision or post collision? If you any point you see an obstacle or an collision point, and if you see a debris of the glass pieces or marks prior to the three-wheel skid mark or post that, that means you can clearly understand that the accident happened previous to the collision point. Okay, so post collision, you have the debris and the windshield pieces, shattered pieces of glass, and then you have a three-line skid mark. That means the skid happened post collision. Okay, so this is really important because you need to identify whether it is pre or post. Then only you will be able to identify what product it was. Okay, so now I will get into a small the accident which I showed. That was the real accident in Mumbai-Pune Express Highway, and the accident which I shown here. This is what has happened. So if you just have a quick look, the car entered in this direction and then it went on, and then it had a final position somewhere here. Okay, you can clearly see the brake, the skid mark here, and then again the skid mark is continued towards the grass, and then the final position of the vehicle is rested here. Okay, so now the initial situation, the driver lost control due to oversteering. The reason could be many. Why did he oversteer? And then you have a collision, and the collision could be a simple landing over of the vehicle, or could be a collision with the pole, or could be a rollover. So maximum of truck accidents rolls because the CGs are much higher, and then the loading conditions is so different that you get a little bit of spin over the vehicle, then you have a total rollover of the vehicle. But in car, not so much, but still we see like 50 to 60% of the accidents prior to the collision only with skidding has a rollover. So rollover, loss of control happens in two main mechanisms. One is oversteering and understeering. Oversteering is the vehicle is spinning the rear axle of the vehicle. If you see here, when you're driving a curve, you will experience that if you're trying to steer your car towards your right, the rear end of the vehicle is pulling out of the vehicle, and many people say it's banking. It's because of centrifugal force, centripetal force, and everything. But the real truth is the yaw velocity is too large that the vehicle is not able to keep the vehicle intact to the line of the motion. So now the point is the same happens in the opposite way in an understeering. You try to negotiate a curve very quick, and you give the yaw velocity too small to the steering wheel, then the vehicle try to tend to roll inside the curve, right? So this is understeering. These are the two important conditions of the loss of control accidents. That's where you have to stabilize the vehicle. How do you stabilize the vehicle? I will explain you in the upcoming slide, right? So as I said, this is the accident site. What do you see here? And this is the same case. I'm talking about only one case. I'm explaining you in detail. And you see the damaged cars here, and also, yeah, unbelted occupant with an impact on the windshield. And you see the long stream. I showed the previous picture started from here, and then the vehicle ended here. The skid marks is almost like 60, 70, or 100 meters before it. So I'll just show you how exactly this accident happened. So he saw another truck, then he tried to steer to its right to avoid an accident or try to overtake. We don't know the reason, but the vehicle completely lost its control, and then it was off the track. And this is a seriously injured case. Yeah. This is how the roll happened. And all these evidences are marked. What you see is the data which is reconstructed from the PC crash. And it's just not an animation. You have close to 250 parameters embedded into it. And then the whole accident is reconstructed. Okay. Now, what are the real root cause of accidents in specific to India? Whatever I'm talking is specific to India. So India, you see human error, infrastructure related, and also, but again, I divide this into two phases, pre-crash and post-crash phase. In the pre-crash phase, it's mainly human error, and then an infrastructure related. In a crash phase also, it's infrastructure related. And the point is, you cannot sum it up because it's individually analyzed. In human error, you have overspeeding, driver inattention, and drowsiness. And also, it's quite obvious that a sleepy driver gives a sudden jerk, then the vehicle again goes for a toss. And a drowsy driver also gives a sudden jerk. And overspeeding, definitely sometimes it's real hard to judge the oncoming vehicle. And infrastructure related, you do not have a poor marking, poor banking of roads, especially in the curvatures and the slippery surface and the roads. And oversteering situation is also related to an object man-made impact and trees and intrusions. So this is another important factor which is seen quite evidently in India. You have a loss of control after the first collision, because if you have seen concrete boulders, which is kept as a median demarcation, when the vehicle loses its control, the first impact which happens is to that concrete boulders, and then this concrete boulder initiates the roll or initiates the loss of control. So that means we are artificially imbibing a lot of systems into the mechanism of accident, that by giving such kind of unscientifically designed infrastructure, we are creating more and more severity, or we are adding more and more severity to the crashes. Okay, so human error is 95% is only due to the loss of control, because steering is either given on the right or on the left. Then you have the differential yaw, and then the vehicle loses its control. And then also due to poor judgment about the curve angles and other things, you may not be able to give a right angle to your steering, so that the vehicle loses its control. So these are the real root causes of accidents in the loss of control accidents for the car crashes. And obviously the mechanisms is similar to any vehicle type if you take even for trucks as well. So now let me get into a working principle of ESP, and lots and lots of videos are there to understand how exactly electronic stability control work, and also previous engineers and also the panelists explained about, showed different sets of videos. I do not want to bring in video because you're already seeing me in a video. So that's the reason why I wanted to give you a real perspective of how exactly the system works through just a small explanation. So it just consists of 5 different components. One is hydraulic unit attached to the control, any ECU you can consider. Then you have a wheel speed sensor, steering angle sensor, and yaw rate sensor. Yaw rate sensor is usually on the steering, steering angle, and yaw rate is usually in the middle. And then you have the ECU which decides. So whenever the vehicle is losing its control, if the vehicle is going, suddenly you see an object here, and then the vehicle tries to counter steer either to the left or to the right, depending on the driver's intention. When the driver is trying to steer to the left, then the vehicle is obviously responding. If the steering control is a little bit more than what is intended to do, then the vehicle may not behave how the driver has to behave. Then can you see here that the intended vehicle has to go in this direction, but the red is the direction at which the vehicle is slipping away. And if this becomes more, then you only have a direct straight collision, and you have the clear yaw mark on the road, and then it loses the control. No matter what driver brakes, whatever driver does, it's impossible to get the vehicle back in control. Yeah, once it moves out of the slip angle, the minimum intended slip angle, that is the yaw rate, which is measured by yaw rate. So now what should we do when we have such kind of a system? I will go back to the slide which I showed here. So here, what you see here is when the vehicle is trying to slide above, now it's a basic physics that you want to get this particular vehicle back in traction, right? So what should you do? You need a counter force which has to act exactly opposite to the vehicle behavior. So if you apply brakes to all the 4 wheels, again, it will induce additional yaw moment to make even more severe slip. So that's the reason why for oversteering mechanism, you have the right front wheel brakes, yeah, as you see here. So you try to brake one wheel, then you have a correction. Again, try to brake another wheel, try to have a correction. So thereby, you are trying to give a differential corrections by understanding the yaw moment to keep the vehicle in traction. Same happens in understeering, but you do the braking to the right rear wheel, not the front wheel, because you need to get the traction back to the control. So this is a simple mechanism. So ESP just works on 2 principles, that it understands the slip angle. If the slip angle is more than what is degree required, then you try to brake the front wheel if it's oversteering. Then you try to brake the right rear wheel if it is understeering. Then you get the traction back. Now, can human do this individually with a very short span? No. This is where this technology comes into the picture, right? Okay. So that's how ESP works. So it's simple. So now, what is its relevance for India? Now, this is the real challenge when I started working on it. Like when we drilled detail into the loss of control accident, most of the loss of control accidents is single vehicle accidents. That means the vehicle is driving, driver either loses sleep, or he tries to do a understeering, try to overtake, what happens is without a secondary impact to the vehicle loses its control and just hits the barricade or to the way. Now in India, the complex problem is that nobody reports a single vehicle accident. If the car is alone, it hits with a tree, the reporting does not happen, because Indian system is designed in such a way that for an accident, two parties has to be there. One should be the guy who met with an accident, the victim, and the other one is the causer of an accident, right? But in single vehicle, it's not there. Then when we drilled into US and Germany data, we saw 40% or single vehicle accidents because they have a proper recording system. When I was about to do this electronic stability control analysis, I saw less than 2% of accidents of loss of control, and that too non-reported. That's where we identified there's something wrong. Then we drilled into most of the details, and then we did a representative analysis of how exactly this data can be weighted. And what you see here is what exactly India is today. This research is again released with the representative analysis for India. How you extrapolate this 5 different locations, the whole of India, is what we discussed in it. So what you see on here is that it's almost like 270,000 accidents are involving car with casualties. That means that is reported. Okay, and then you have 857,000 is the total car accidents with casualties, and overall accident is 1,286,000. That's how we call it, almost like 1.28. Now the point is when you extrapolate 269,000, that is 270,000. Let's keep it and make it 100%. And then in 100%, we try to again divide that. How much percentage of accidents are single vehicle accidents? Need not be single accident. The skidding prior to the collision. That means irrespective whether it crashes to another car, or whether it crashes to a pole, or whether it crashes to a barricade. My topic is to identify whether the car skids prior to the collision. If it's post collision, I will not consider here. Okay, because that's the secondary mitigation that we can talk about. This is the first mitigation, that is prior to the collision. Then this filter happens, and we saw close to 15% of the cars are due to loss of control. That means in India, 41,000 car crashes occurs due to loss of control of accidents. I hope I conveyed how exactly we extrapolated the overall study for India. Okay. Now the question comes. There is a lot of debate and discussions in many of the countries and other people. They say that, okay, ESP is only because of the skidding, icy conditions and this, and it only operates at, say, winter testing levels at minus 50 degree and some other thing. But the real fact is no. The most of the accidents, what you see, 88% of the accidents in India of loss of control are when it is clear and dry weather. You see here, this part, you see almost 88%, 36,000 accidents happen in a clear weather, and rain conditions is only 12%, but still there is a loss of control. That means, okay, ice and slippery condition may add to the skid, but that's not the only prerequisite to say that ESP is required only on the icy conditions. Then you can see when are the daylights, usually daylight is higher accidents. That's maybe because the data collection is only during the day and other thing. But what's important thing which I wanted to say here is, if you have a quick look on this, you see 14, that the straight road, the bottom is the code of the pre-crash events, and the top is the percentage. So now if you see here, the straight road, we have 36%. That means there is no obstacle. The vehicle is only straight. The road is very straight. The visibility is very good. But still vehicle loses its control on the straight road. That is close to 36%. That means it's a human error where is either sleepy, overtaking, or doing some kind of consideration. That means it's independent of infrastructure, some technology needed in order to intervene to avoid such an accident in the straight road. Then we get into the curved roads, and then we get into the right turn, then on the zigzag curves, overtaking mechanism, on frontal collision, longitudinal traffic, then rear end crashes, then animals coming in front. Again, for surprises in India, this is really high, around 3%. And then overtaking when another vehicle is available, changing lane on the wrong, left to right. 2 out of 3 crashes occurs at daytime on a dry and street conditions, which is already explained. And every second loss of control crash is a single crash event. That means if I have 100 cases, that means 50 cases are single crash, single vehicle. That means nearly, again, around in that 50 out of 100, around 40 cases are not reported. Okay. So this brings me how a technology can avoid. As you see here on the left side, you already saw how exactly this technology works. On the right side, you see the vehicle is vehicle is made to brake on the front right wheel, and then you have the vehicle back into the traction. That's how the vehicle is brought back to the control. Not all accidents is avoidable, but a certain percentage of accidents is really avoidable with electronic stability control. And what you see here is the real impact of how exactly the one particular case which we are following through the stats is avoidable through this particular accident. Now, in most of the panel, we have a same question that what is the cost benefit? Okay, this is a very big question we could not answer almost since a decade. Okay, because if somebody can say what is the cost involved if one person dies in an accident, we do not have this number. If you compare to the Western world, you have this number released either from the Ministry of Home, Ministry of Health, Ministry of Internal Affairs. But in India, there's totally different numbers. Insurance guys say some other number, and Indian Statistical Institute say some other number, and uniform number was not available. And we took almost like 2.5 years to study close to 300 reports across India and the globe, conducted close to 150 interviews on phone calls and other things during the lockdown phase. And we estimated socioeconomic loss for India altogether, independent of car. This is a generic paper, which does not talk anything about the technology nor the product, which is released just prior to the this conference in SIAT 2021 and bagged the best research paper award. You can all refer, it's you can download and have a look. But I took a small snippet from that particular report and try to map this against loss of control and what is the real root cause of accident. So we identified first what is the cost of single accident for different vehicle types, and we used 3 different methodologies, and close to 60-70 parameters were used, inputs were used to derive this number. Now the point is, like the fatal cases, especially in 2019, fatal people, not fatal accidents, it's fatal people, around 5,300. Sorry, fatal accidents, not people level. This is at the accident level. It's around 5,300, which is a counted average. And each car accident costs you around 160,000 accident. If one person is fatal in one car accident, independent of what type of accident, in this case, it's loss of control. That counted me 5,300 loss of control in India in 2019 reported. Again, I'm specifically saying reported accidents. This constitute for one particular accident, the car accident, if one person dies, then that is 168,000. And how we calculated, refer the paper. Then seriously injured is around 17,000, minor injury is around 7,500, and no injury is around 500, because we did not consider no injury because it's extremely difficult to get no injury data. Then this constituted, then we multiply 5,300 against 168,000 to derive close to $1 billion. So total economic loss of a loss of control accident constitute for India is $1.26 billion per annum. That is exactly in 2019. Okay. Now we have the numbers. You name which product you wanted to do a benefit estimation and a cost estimation. We will give you the numbers. And I also request the panelists and also the participants to take up this paper and then try to read it. And you are free to develop some more methodologies on top of it. And this is the base of the method. This comes to the last slide to clearly discuss about the loss of control accidents, and which is common in India. And the only thing is, it is not reported. We have to be really specific. There are few more type of accidents which is really not seen, but that is killing so many people. So accident research, the real root cause analysis, going to the scene, doing a Sherlock Holmes work is the real thrill in identifying what is the really important in it. Then the root cause, inappropriate speed, drug abuse, visibility condition, but less impact through the weather condition is clearly derived out of this particular study. The potential is up to 33,000 accidents with total numbering 20,000 road fatalities and severely injured. So it's clubbed again. So it's road fatalities and severely injured together. 20,000 people could be altogether avoided with electronic stability control. As I said, this is one line, does not belong to this particular study, but this comes from the research latest. To give the link for the next line, social impact for the road accident crashes starts up to $38 billion. This is the first time ever we did this study, which constitute 1.35% GDP annually. Thereof, electronic stability control and the relevant costs constitute about $1.26 billion per year. This is only the vehicle estimated. Still, infrastructure and the human cost is not added to it. If you add, then we have another number. ESP facts, which is already published by Bosch, 80% of all skidding accidents, irrespective of the region, irrespective of the country, is all the skidding accidents can be directly avoided by electronic stability control. For more information, you can refer to the benefit estimation of electronic stability control in SA International. 14% of all fatal car accidents are skidding car related. Furthermore, we are not saying that only ESP will avoid all the accidents by when you put into the car. We need an education and safety awareness to optimally define the speed, and driver awareness to really understand what is the real root cause of accidents and enable him to avoid an oversteering and understeering wherever it is possible. And definitely there is a huge input that we have to give for infrastructure. I mean, we already did this to the Ministry of Road Transport, to the local authorities, not to make it more severe by adding certain unscientifically designed roads in order for the beautification, which will add more and more problem to the severity of the accident. And of course, rescue and the post-crash response has to be harmonized. With this, I would like to close my talk. I hope I gave you an overview of accident research and what is the real root cause of loss of control, what is the loss of control and the real root cause of it, and how it is relevant for India, and finally the benefit and also the socioeconomic impact of this particular topic. And I'll be more than happy to have a couple of questions if it's available, or my mail ID is available. You can also drop me. Thank you very much for Mobility team for giving me this opportunity and for this wonderful session. Thank you.
Thank you so much, Mr. Kumaresh. We have a few questions for you. First question is from S. Mohan. How can we detect, Mr. Kumaresh, are you there for Q&A?
Yeah, I'm there. Sorry.
Okay. So first question is from Mr. S. Mohan. He wants to know how can we detect loss of brake control, distance on ABS control, as there cannot easily be detected tire mark as footprint.
See, any ABS, any vehicle which is equipped with ABS, you will not see a tire mark straight, because the technology itself will not allow the vehicle to jam, right? So when you have a tire, when you have an anti-lock braking system, you see, you go to the road, click a photograph. Naked eye you cannot see. Click a photograph and see. You will have a staggered manner of brake mark. You have one strip of brake, next one strip of brake, next one strip of brake. This runs along 20 meters, 30 meters, 10 meters, how much ever it is. When you have a staggered brake mark on the street, two parallel, I'm mentioning it's two parallel, that is definitely a brake mark with a vehicle which has an ABS into it. That means the vehicle did not completely lock the wheel. That means you have locking and unlocking pattern. So what you are questioning in your head that there is no brake pattern when ABS is there, that means you will not see a brake pattern at all when you have an ABS fitted into the car.
His follow-up question is, if ABS already controls to reach braking to maximum limit, then how can we control additional braking during oversteer control with ESP?
That's the point. We are not braking the vehicle at all. If the vehicle is beyond a certain slip angle of a yaw, okay, say some theta angle of say 5 degree or 6 degree, the vehicle is completely under skid. You apply a complete brake, no matter what super technology you have, ABS, advanced ABS or whatever ABS, vehicle will not come into control. But I explained how exactly you have to get the back in control is by braking only one particular wheel to the right front wheel when it is oversteering. Okay, sorry, left front wheel. And for the understeering, you need the right rear wheel. So that's the only way we can get the car control when it is completely over the loss of control. So that means braking plays a role before the loss of control. Once the loss of control, that means the vehicle moves out of the slip angle. There is no point that even brakes can help. Only ESP has to kick into the feature.
Thank you, Mr. Kumaresh. Now, before inviting the next speaker, I would like request Vivek to play the highlights of our track day event.
Thank you, team. All the best.
Thank you so much, Vivek. Now I would like to invite Mr. Varun Arora, Deputy Manager, Hero MotoCorp, to deliver his presentation.
Yeah, hello everyone. I'm audible.
Yes, Varun, you're audible.
Yeah. So thanks for giving the platform, such a great platform where we are discussing on the dynamic part, which is very critical nowadays. And even when you start working on the development and the dynamics, you will always attach with the things. And more of the panelists which we had in the morning session, Kaniappan ji, Sathish ji, and then Mr. Just now I forgot his name, Girikumar ji. So all given the platform to set what things are going currently trending in the market. Let's start first. It is on the feature side, and then moving to the suspension dynamics, and third accident. That how these features are linked with the accident. So I'll be starting with my little bit introduction. So myself, Varun Arora. I am basically working in Hero MotoCorp, handling two-wheeler project for the ABS and all its feature. Prior to this, I was working in Mahindra where I used to handle ABS, ESP, and ADAS. And if you can see right now, market XUV 700, that was my keen project where I worked. And right now, I'm working on many projects at Hero MotoCorp, which is going to be launched soon. So I'm basically from Himachal Pradesh, done graduation in mechanical engineering from Maharishi Markandeya University, Ambala. And post that, I got recruited through Baha. Many of maybe engineers who joined here must be linked with Baha. So I could say that is the best platform which SAE has made to interact dynamically with the vehicle, interact with the experts, and get into the that things. So I would be today presenting on ABS. So basic ABS I would be discussing. We discuss on the feature. Now I will be discussing more on the ABS two-wheeler part. So I'll be presenting. So let me know once my presentation is available. It is
Yours,
visible.
your presentation is visible, Varun.
Yeah. So so basically, I'll be keen touching on today on the ABS part where we will be discussing on the basic concept, interface components which are working along with the ABS on the two-wheeler part. Working principle will be the more focused slide we'll have, and then types of ABS in two-wheeler which we are currently having in the market or development is going on. Six is features which we are related to ABS. In four-wheeler we will call it ESP ADAS, but in a two-wheeler we used to call with ABS HECU itself we are controlling all the stuff, even though ESP is also integrated with ABS and its stability thing. But in two-wheeler industry we used to call it ABS HECU, which having the some features which help you in stability, give you more feeling of the comfort and power enthusiasm of riding a bike with different mods. So all this will touch on. So first introduction. So as we all know, anti-lock braking system. Usually, I think if we call 10 years back, we can see on the like brochure of the all the OEMs, they mention it as a ABS additional in this variant, and we used to call this is a simple feature which is companies providing to all the stakeholders, and for that they are charging some amount for the same. But when the Indian government and everyone realized that ABS how it is helping in the fatal accidents and which is causing directly to the deaths and thing. So then Indian government has made mandatory from April 2019 that ABS will be applicable to all the four-wheeler personal segment and two-wheeler above to 125cc. So basically what ABS do is avoid the slip. So you can see on the left side the picture, we have without ABS and with ABS. So if you could see the first image, the person has applied a panic brake, or it can be a low mu surface where the friction coefficient is very less and a tire can lock easily. So when he applied the brake, he lost the control and hit on the object or fell down, or because he fell down, someone hit from the backside. So two-wheeler, somewhat ABS tuning, ABS calibration is very critical I would say a four-wheeler also, it's very critical because you have to control four wheels. But here the only two wheels, and then the balancing has to be maintained by the rider more side. So second, if you see the with ABS, the person has applied the brake, and even with the locking of the wheels with the ABS actuation, he could easily steer the bike and move sidewise of the object. So this is why ABS is required. It helps in controlling the vehicle when the wheels got locked. Because once even I faced personally doing during the testing when initially I joined. So I was doing a testing and it was with the rear system only, front fail, and I did a panic brake and the vehicle turn around 360-degree. So it is very like testing part is very important in ABS tuning. Anyhow, simulation parts also going on, but testing part is very important in that. And moreover, with ABS, we are getting the whatever the rider wants to. For example, for performance, we are also getting in line with that, and also the stability we are achieving, which ensures the safety. So this is the introduction part. And now I would be going to the basic concept how ABS actually working. This is I'm discussing on single channel thing because it is similar to two channel, four channel, which is in the four wheeler. So what will happen? So initially our ECU, we call it as a HECU, which is hydraulic electronic control unit. And why it is called HECU? HCU plus ECU means electronic also and hydraulic valves are inside. So we used to call it HECU, and in four wheeler we call it as ESP, ABS, different HECU, HCU. So that's the naming of different tires one and OEMs to rename the object in their portfolio. So basically first ECU will detect the wheel. So wheel, how it will detect the slip. For example, if I talk about single channel, there is a slip when user applied a brake. So there are deceleration values we are getting. So with that deceleration, system will detect whether deceleration drop is a smooth or sudden. Based on that, it will calculate the slip. When it calculates the slip, there is some slip is depend on the totally vehicle dynamics and how you want the vehicle to behave. It you want to be more performance side or you want to be the more stability side. Both are inversely proportional. If you are going towards performance, you have to compromise with the stability. So ABS will detect the wheel spin and wheel slip, and then it will give internal calculation to its ECU. Into ECU will do some calculation and send it to the HECU to open the valve and close the valve. So in single channel for each wheel control, it required minimum two valves to work the ABS along with the motors. So this is the basic concept, which is for the starters as well as who has already learned, say, they can also remember the things. Then second, we'll be moving to the interface component. What are the interface component required for the ABS to work on properly? So there are, I would say for ABS alone in a two-wheeler, there is sufficient if we are getting a toner wheel with a wheel speed means input from the wheel speed of the wheel input like pulse rate to the ECU and power supply, that is sufficient for ABS to control the vehicle. But when we are moving to the features, for example, now you might have seen in the brochure of the OEs, we are getting the ride modes, we are getting the traction control, we are getting the this cornering ABS, hill hold control, many things which already there in the OEMs, which ESP is handling all this stuff. But here we would be in ESP. If you could see, there is one I have mentioned IMU. So inertial measurement unit, what it does, it will give you lat, yaw, longitudinal pitch inputs to the bike so that he can control during cornering time how much braking is required. So these all stuff required input from the IMU. But while in case of electronic stability program, there is already an integrated sensor which is inside them. So basically, these are the primary interface which is required to work ABS to work properly, and these are the additional things which is required for ABS to perform with the features. For example, engine ECU. If you see the ride modes, it is linked with engine, then your instrument cluster, then your ABS, and then traction control also come into that ride modes. So moving to the next step, so which is the main focus slide for today. So now working principle. Basically, what ABS is doing, it is doing the four steps. One, it will detect the locking. Second, there are three steps. How, as you know, ABS one of you have testing background, if you have ride any four-wheeler, two-wheeler, you must have feel there is some pulsation. Pedal is going down, pedal is going up, pedal is holding. So all these things you are feeling because of the HECU walls, which is there. Solenoids walls are inside the HECU. So all these control the ABS and helps to perform the stability. So we'll go first. We'll see this curve. Hope you can see my mark. So how the ABS will detect where I have to come back, which reference I have to take. So basically in HECU, while doing the calibration on the dynamic part, we used to check the locking deceleration, and even it is available in the theoretical part also. So once that is available, so user will start its calibration, and ECU will set a reference speed based on the drop of the wheel speed, which we are getting signal from the wheel speed sensor. And what it will do, see, so here the locking tends to happen. So here we are seeing the pressure increase. It means user is providing hard braking, or maybe it is on a low surface. So first it will do, ABS will come into the picture. It will decrease the pressure, and then it will hold the pressure, and slightly it will increase the pressure. So this increase decrease will help you to maintain that deceleration without locking and maintaining the stability of the motorcycle. So this how the curve moves, and even you 15 to 20 times in 1 second ABS can actuate when you are going for a hard braking. So all these things are internally calculated by ECU and give the command to the HECU walls to open, close, like that it will go on. So if you could see the left hand side, so this is the basically image of a single channel. But when we move to two channel, it will be additional two walls for that wheel, and four channel additional four walls. So total 8 walls will be there in four-wheelers. This is for the single channel system, which I am going to explain now. So basically, if you could see, this is the first inlet wall, which normally remains open. So, and second one is an outlet wall, which we call a normally closed wall. And third is your low pressure accumulator, which accumulate the fluid which cut down during the pressure decrease. And third is your pump, which will pump back the fluid to the master cylinder, where you will feel the pulsation on your pedal that something is hitting me back. So that's how this thing works. So I would be going one by one condition. So this is the normal braking. When normal braking, your inlet valve will remain open, normal valve will close, and LPA pump will not work. So when you are doing a hard braking without ABS, what will happen? So this inlet valve directly send brake pressure to the wheel, and even the braking, if you utilize the complete tire friction, so your wheel tendency will go for a lock, and you will lose a control. So this is the scenario of the hard braking without ABS. But when you are going for a pressure decrease, for the pressure decrease, your inlet valve will close, and your normally closed valve will open, and it will accumulate in the LPA, and pump will start working to pump it back to the master cylinder. When we go for a pressure hold, so in the pressure hold, the same thing, this will hand lever will be in the one condition, it means it is a press, and inlet valve will remain closed, and outlet will also remain closed, so that pressure should maintain whatever you want to hold in that. And pump parallelly will be working to throw out the fluid which already is there in the pressure decrease. Third is pressure increase, which is also important because we need to uh, stop the vehicle in that time without impacting on the stability. For that, your inlet valve will open, and your normally closed valve will close, and LPA will pump the fluid to the master cylinder through inlet valve. It will come to the. So that's how the basic ABS work with the different valves actuation, and the pump is always common. Like for example, two channel also, no pump will be one, so only two wall addition will be there, and parallelly LPAs. And this is the basic structure which will extend with four-wheelers, two channel, four channel. So this is the basic working principle how ABS actually works to control the wheels locking. So now we'll be moving towards the types of ABS which are currently we have in our two-wheeler market. So first is single channel with one wheel speed sensor input. So basically in this we have a ABS on a front side, and we have a one speed sensor which is giving input to the HECU, and it is internally logics are there which are detecting whether wheel in the locking condition or which kind of a surface it is going based on the drop in the wheel RPM. And second thing is single channel with two wheel speed sensor input. Basically, single channel with two wheel speed sensor input also work on the same functionality. Only thing, we have another reference point of the wheel RPM of the rear, where we can easily detect whether there is a false trigger or it is a okay trigger. It will improve further tuning, fine tuning in terms of feel, pedal, your lever feel, and all these parameter. Third is dual channel. Dual channel simple, like we have a single channel. Secondly, we'll add the rear also for the ABS, and both the wheels can be controlled individually for the ABS based on the brake application from the lever side or a footrest. Fourth one, we have a combined ABS. So this is a new technology where some OEMs already implemented and some are already going on. So basically, this combined brake system is normally, like usually we in Activa, we have a combined braking system. Similar to that, this is also helps in making the weight transfer common. For example, if you're applying a front brake, your weight transfer goes to the front, and there is a tendency that rear will lose some traction and tries to lift off. But in combined ABS, it will split according to the tuning requirement from OEs. So these are the four types of ABS which we have currently and which is going to come soon or later. So these are the types of ABS. Then we now ABS, we know the safety point, but anyhow, safety plus features is always kind of a attraction point to the user. And also with these features, there are some features which are actually helping in the stability of a motorcycles, and giving you an option to select the ride modes, traction control, which we have in four-wheeler. So all these features are currently there in the market or going to come. And sooner or later there will be ADAS technology also will be coming on the motorcycle. As we could see, four-wheeler XUV700 is one example. Gloucester in India, it is till now working as fine, because there are a lot of data we need to take for the ADAS tuning, how the system detect it is actually a person obstacle. So all this play a vital role while implementing this feature in the market, because it can give you a negative direction also. So moving to the features, we have a rear lift wheel up protection. So if you could see the right image, applying the front brake, your wheel got lift up. Sometime there is a chance that it will roll based on your vehicle dynamics. So during that time, what ABS will do, it will cut down the pressure on the rear side, maintaining the performance, cut up and down. Then rear wheel will not lift up because your weight transfer will not go front, and rear will tendency lift up will be low. Then second, we have a ride modes. So in the ride modes, if you could see in the many of the uh, templates, we have some rain mode, race mode, sport mode, off-road pro mode, something like we are using, getting the market abbreviation that these are some of the modes which is there in the vehicle. So basically in the ride modes, what actually we have different map of ABS. For example, you want ABS to pitch in later, you want ABS to control early intervention, you want ABS to behave normal, you want to cut down ABS on the rear wheel. So all these can be controlled through ride modes. And then we have third one is cornering ABS, where cornering ABS is usually, if you could see the third image, while cornering, there are chances that your wheel get slipped because of loss of traction, and resulting in the customer or rider to fall. For that, we have a technology ABS with IMU. So in four-wheeler, we have integrated sensor, but in two-wheeler, because of a packaging till now, we have a separate input sensor, which I showed in the interface component slide, IMU. So it is basically give you an input of pitch angle, roll angle, yaw angle, and with that, ABS is maintaining the braking so that your vehicle should not slip and you can easily corner the brake. But for the enthusiastic like racing, we used to switch off this feature because that their time we have to meet the time everywhere. So these are additional safety feature, but for the racing way, we used to not give this feature, and rider not use this feature while their races. And the fourth one is your traction control. Similar to that, when we are doing a harsh acceleration, our mostly motorcycles are rear wheel driven. So when you do a harsh acceleration, your rear wheel will spin. It will spin at faster rate. So what HECU will do, it will see the comparison of the wheel speed of a front and rear, and see whether wheel is spinning. Based on that, either ABS will give a request to engine to cut down this torque, and that torque will be maintained by our EMS by using the fuel injection, by cutting down the fuel injection flow. All these thing will be controlled by engine, but basically request will come from ABS HECU. There are some technology which we are directly through engine, where engine is directly monitoring the wheel speed and calculating the engine torque. So that's depend on the OE strategy, what they want to follow to implement that. Moving to the next feature. So next feature, as I discussed in our type of system, there is a combined braking system. So with the additional cost and thing, we are getting HECU separately, where the separate walls or the working logic will be different to work as a combined braking system, where front and rear wheel both can be controlled, vice versa. For example, if you're applying on a rear, you can split the distribution on front. That depends totally on the dynamic and the rider requirement of the OEs. Second is your wheelie control. We could see in the image that while doing the harsh acceleration, bike tendency is to lift. So for that also, similar to TC, we are giving the torque request to engine, and engine is cutting down the torque through management of the fuel, and through which we can control the bike stability. Then moving to the hill hold control, in four-wheeler, it is already there. When, for example, when you are on a hill and suddenly the traffic stops, so there is always a mind in the customer that I have to pull down a handbrake so that I can easily drive away. But when these features come, like hill hold control in four-wheeler or two-wheeler, what it will do, it will apply a brake for 2 seconds post your release of the brake pedal or a brake lever, so that during that time you can easily release the clutch and go beyond. This time we can increase, but anyhow, if we increase this time, it will impact on your clutch performance and all. So the optimum time is 2 to 4 seconds, which OE prefer, depends on their vehicle requirement. And then this is last, we have drag torque control. So this drag torque control is also like when we used to sometime when we are riding, and there is some right now we have a good modularity in the bikes that this sudden shift will not happen. But some user used to do by suddenly increasing the RPM, where your torque will increase on the wheel, causing the drag on more in the rear side and cause the slip. So for that also, ABS can give a torque calculation to the system, and engine will follow that. So basically, all this feature ABS currently we have in the market and going to have soon. So thank you. This is my last slide.